Hello class, this is a continuation on dilations. In this video, we're going to be applying these to relations and their graphs. In comparison, in the previous video, we were applying these strictly to functions, but now we're going to demonstrate that you can still do this even if it's not a function. As we saw, to dilate vertically or dilate horizontally, we are substituting x or y for y over a, or x over b for the required dilation factor. Now remember that graphically, dilation means to multiply the distance of points from x or the y-axis, and this can still apply to non-functions and to their graphs. So let's go straight into our first two examples here. So let's take a look at a vertical dilation on this circle. So this is definitely not a function, but we can still apply the vertical dilation. Now remember, the vertical dilation here, y over a. In this case, it's going to be y over 2. But now when we substitute this, we get x squared plus y over 2 squared equals 4. When we expand this one, we get x squared plus y squared over 4 equals 4. Now this is definitely an expression that we don't know what this looks like, but looking at this graphically, it means that the points, the y distances from the x-axis, are being multiplied or dilated by a factor of 2. So this y point here, which is 2, will now become 4. This point here, which is negative 2, will become negative 4. So this is 0, negative 4, and this one is 0, 4. These points don't move since the distance from the x-axis is currently 0. So multiplying that by 2 doesn't do anything. So now, just looking at this, what this is actually is an ellipse or an oval. So it looks something like so, but it needs to be a lot smoother. So let's just use my iPad's feature to do this. Now the iPad has a hard time trying to line it up perfectly vertically, but it should look something like so in blue. And the center remains the same. And so that there is a vertical dilation to a non-function. Let's do this now to the x-axis, or the horizontal dilation, by a factor of 3 this time. Well, for this one, since it's a factor of 3, it'll become x equals x over 3. Substituting this, we get x over 3 squared plus y squared equals 1. This will then become x squared over 9 plus y squared equals 1. Same deal for this. What this means is that the distance, which is currently 1 in the x distance, is now being multiplied by 3. So this point will be stretched out 3 units to the left, or times by 3. So it'll become this point here. That coordinate will be negative 3, 0. And likewise for this one, this will become positive 3, 0. And like the other one, I'm just going to copy this, make it a lot easier. I'm just going to rotate this like so. And so the graph should look something like so. Let's just move this a little bit across. Obviously not to scale, but I think you get the idea that these distances are still being stretched away by the factor of 3. Let's move on to the next two examples. These ones, we are dilating it or multiplying it by a quarter this time. So let's take a look at what happens when we do this. Now, since it's a vertical dilation, we are substituting y equals y over a. In this case, it's going to be y over a quarter. Now, I hope you're getting more familiar with this. This is essentially, we are dividing by a quarter, which is the same as substituting y becoming 4y. So this can become x squared plus y squared equals 16. And we're going to substitute now for y. This becomes x squared plus 16y squared equals 16, which we could simplify a bit further, but we can just leave it like so. Now, graphically, what this means is, since we are dilating vertically by a factor of a quarter, we are multiplying the distances of y by a quarter. So what was once 4 is going to be, well, times by a quarter, which would be 1, which would be half, then half. So approximately around here and here. So the coordinates of this one would be 0, 1, 0, negative 1. And again, we could just sketch this something like so, but to make it easier for myself, I'm just going to grab this one and just paste it on here. So it should look something like so. So that there is a vertical dilation by a quarter. Now, seeing this, you can try it for the next one. It'll be the same idea. This one, once again, we are substituting y equals, since it's a horizontal dilation, it's x equals, and we're substituting x over 1/2. And as before, this is the same as x becoming 2x. Substituting this, we get 2x squared plus y squared equals 100. This becomes 4x squared plus y squared equals 100. Now, once again, because this is an unfamiliar relation or equation, we can instead just look at this graphically. So the horizontal dilation, once again, means we're looking at the horizontal distances and halving them as a distance from the y-axis. So this x distance of -10 will be halved to become -5, 0. And this point here will also be halved approximately here to become 5, 0. And just again, to keep this nice and easy, I'm just going to borrow this one, stretching it out, squeezing these in. Obviously, it's not to scale, but I think you get the idea. This one's actually a bit off center, but we get the idea of what this is doing. So, hope that gave you an insight into dilations. I'll look into this example later, because you'll see that while these 4 examples were all centered on 0, 0, it gets slightly more challenging when it's off center. Hope to see you in the next video, and best of luck.